Bismillahirrahmanirrahim. Welcome students to the online lecture of Digital Logic Design. And in today's lecture we will be discussing the standard forms. In the last lecture we discussed the Boolean functions. In the current lecture we will be discussing the standard form representation. This part of the course belongs to the course learning outcome 2. We will be explaining two new terms here which we define as the min term and the max terms. In a min term, an and term consists of all literals in their normal form or in their complemented form. For example, say if we have a binary variables x and y, then their min terms could be represented as xy complement, x complement y, x complement y complement. If you see that these are actually all the combinations that are two variable system forms, like 1 1, then it's 1 0, then 0 1, and then 0 0. So if you actually represent all these terms in form of x or y, I mean x is representing 1, and while if we are representing the x complement, then it's represented here as 0. So if you represent all the four combinations here, it is similar to representing in this way. So these are known as the min terms. It is also called a standard product. And as you know that if you have n variables, then you can form about 2 power n min terms. So if you have a 2 variable system, then you have a maximum of 4 min terms, while if you have a 3 variable system, then you would have about 8 combination that each of the 8 combination will be representing a separate min term. Then there is another terminology we used, which is known as the max term. In the max term, or we can also say it as an OR term, it is also called a standard sum. It is represented in a way like this. Say if you have a 2 variable system, then it is represented as like this x plus y. Again, it also depends upon the number of combinations that a system exists based on the how many variables are present in the system. Each max term is the complement of its corresponding min term, and vice versa. We would see in the next few slides through certain examples that how these min terms and the max terms are actually related. Say for example we have a 3 variable system x, y, z. We will be now representing them in form of both the min term and the max term. For the min term, what we do is first we have to draw a truth table for all the values of x, y, z, which we have done here. You can see that there are 8 combinations here for all these 3 inputs, and if you represent them by adding all these terms in a form that x complement represents the 0, y complement represents the 0, z complements represent the 0, while x represents 1, y represents 1, and z represents the corresponding 1. So, and if you add all these terms, it will represent the min terms, and we will designate each min term as m0, m1 up to m7. And if you look at how this subscript is coming here, this subscript is actually from the equivalent of the binary here. It's 0 here, so that's why here its equivalent binary is equal to 1, so that's why we are writing here 1 as. It is representing binary 2 here, 1 0, so that's why we have 2 here. Similarly 3 4 5 6 7, you can see that all these numbers are representing its binary equivalent. So in the form of, if we are representing any function or special term in form of min terms, then actually it is defined in this kind of way. In a min term, it is a necessary or it's must that you must mention all the terms here, because you cannot write here in the min term x complement y only or xy complement only. You need to represent the z term too. So in the min terms, all the three inputs are included in the representation, and if the corresponding into the corresponding has the value variable has the value of 0, then it is represented by x complement, and if the corresponding value is 1, then it's represented by that number itself, say x. Now in a similar manner, we will be now representing the max term. For the min terms, we have used the small m for representation, and then the subscript m0, 1, 2, 3, 4 up to m7. While for the max term, what we do is we represent it in form of a capital M. So this is will be equal to capital M, and the next will be equal to capital M1, then M2 up to M7. And in the similar way, the same way, its subscript is written, that if you have the equivalent binary of these numbers, it will become the subscript of this one. And if you see the max term is actually the complement of its corresponding min term. You can say that the max term is represented in a form of this, like x plus y plus z, in which if you see that the x is represented in a form of a complement form. In the min term, we represented x as x complement, but when we represent it in a max term form, we will be representing it as x. So in max terms, the 0 is represented as x, and 1 is represented as x complement. So in this way, it is represented. And if you just look at this equation, if you take the complement of this term through the De Morgan's law, the end result would be equal to this one, because you will have a double complement here, which will result again in the value of x. So this is how both the min terms and the max terms are represented. In the min terms, all the values of the variables are ANDed, but in the max term, all the values are ORed. Any Boolean function can be represented in form of min terms or the max term. Say we want to represent a given function in form of its min term. So what we do is, first we have to calculate the basic truth table for it, the function. We have calculated the values, written all the values here, x, y, and z, and after that we are given this equation that f1 is represented as this one. And if you look at the table, or you can just calculate the values here, that this term basically corresponds to m1. How? Because this is 1 here, y complement represents 0, this represents a 0, so 0, 0, 1 means 1. So if we represent it in a form of min term, this will become m1. And similarly, if we represent this will become 1, 0, 0. So it will be representing 4. So we will write m4 here. And similarly here 1, 1, 1. So this will be representing m7. So this function, if you are representing in this kind of form, then you can write in terms of min terms as this one. It means that there are 3 min terms included, 1, 4, and 7. And for these 1, 4, and 7, the function value will be equal to 1. If you see that for m1, m4, and m7, the value of the function is equal to 1. So in this way, we have represented the function f1 in form of the min terms. For the second function f2, these values are written. And now we will see that how we can represent this in the form of the min terms. Actually, the min terms are those values on which the function value is having the output of 1. So we just need to convert this into m0 or m1 or equivalent form. This will become 0, this will become 1, 1. So 0, 1, 1 is 3. So first term is 3. Similarly, the next one is 5. This one is 1, 1, 0, that equal to 6. And the last one 1, 1, 1, that means m7. So the f2 function can be defined in terms of minterms in this way, and you can see that only on those minterms we have a value of 1 here. This is 3, this is 5, this is 6, and this is 7. So this representation is also known as the canonical representations, in which we represent a system in form of minterms or the max terms. Actually, we will be utilizing these terms in the next few lectures, specifically in the K-map thing. Now we will discuss a little relationship that how both of these canonical forms can be related to each other. We have defined that for a function f1, if we express it in terms of min terms, it will only describe the values which have 1 in the output. So if we take the complement of this value, complement of this function, then that's equivalent to ORing all these values which were 0. So actually these are the values which were zeros when we have initially have a truth table, form the truth table, and then we have solved it. Because f1 was originally on m1, m4, and m7. So for all other values m0, m2, m3, m5, and m6, it will have 0 on the output. So if we just take the complement, then complement can be represented by the other min terms like m0, m2, m3, m5, and m6. Now, as we know that if we take complement of a variable or a function twice, then it should again result in the same thing. So what we do is we again take the complement of this f1 complement here. So if you take the complement, apply the complement procedure here, you can calculate that it can be represented here as this one, because from the De Morgan's law, we know that it will become double complement here, which will again result in x or y or z, so which is represented here as this. Similarly, the next term will be multiplied here as this, next one as here, this one as here, and this is the last one, and all these terms will be now multiplying. So as you know from the table of the max term representation, in the max term representation we were basically ending all the terms. So if you see that all these terms are ending with each other, and from the table of the max term you can see that this term here represents 0, 0, 0, which means capital M0. This is representing as 0, 1, 0 as 2, and similarly the next term 3, 5, and 6. So for the function f1, which we have described in the last slide, which was represented in this form, that f1 was equal to sum of minterms m1 plus m4 plus m7. It was represented in the form of minterms, and now in the form of max term it is represented in this way. So this is its representation in form of the max term. So any Boolean function can be expressed as a sum of minterms, or it could be also expressed as a sum of the max terms. Boolean function sum as expressed as the sum of the minterms or the product of max term are said to be in the canonical form representation. But as you know that it's always not happening that the whole function that you are given is in a form of minterm or max sum. Most of the time the functions we have discussed so far are not in the say minterm or max term representation, because in the minterm or max term representation you need to have all the variables in a term. Say if you have a 3 variable system x, y, z, then you need to have all the representation of all 3 variables in the each term. So because you have to calculate this from the truth table, you need to know the value of all the 3 variables. But what if it's not given in that way? So what we need to do is we need to convert this Boolean function into a min term representation. So first we need to represent this function in the form of a min term representation. If you see that we have two terms here, this is the first term and this is the second term. In the first term, if we need to represent only the first term in form of min term, we need to have a value of certain value of b or c here. But we have only one value here, and if you look at the second term here, the value of a is missing. So if you compare it with the truth table or the min term table, we cannot relate it to that. So we need to define a mechanism by which we can first express this in form of the min term. How we can do it is very easy. Suppose for the first term, in the a term, we don't have the b and the c. So what we do is we first AND it with b plus b complement, because b plus b complement always results in 1. So we can always write it here as b or b complement here. So when we will open this parenthesis, it will become ab plus ab complement. And now you can see that in these two terms, now the c term is missing. So in a similar way, in which we added the b term, now we added the c one. And how we added that, for the each term we included a separate thing, c or c complement, which is always equal to 1. So we can put it here, and similarly with the next one here. So we will get these two terms here. And for the last term, you know that we don't have a value of a here. So we can similarly, in the same way, we can add a value of a here in this way. A plus, we can write here as a plus a complement. And if you open up all these parentheses, it will result in these terms. Now if you look at these terms, all these terms are in form of the min term or the max term representation. And you can represent it as very easily, that say you just arrange it. This is the a complement, so it will be basically representing the 0. This is the b complement, it will also be representing the 0, and this is c, it will be representing the 1. So we will have m1 here. This is equivalent to 100 or 100, which is equal to 4. So next is 5, then 6 and 7. So this function can be represented in form of min terms like this. For the min term, we use this summation, because of the ordering of all these terms, we can represent this in form of the summation. So if we want to represent any function in form of min terms, we can write it in this way, or a more standard way or easier way is this one, that we write it as the summation of all the min terms on which the function has a value of 1. You can see that its value is on 1, 4, 5, 6 and 7. For rest of them, its value is equal to 0. Now in a similar way, say if we have to express certain Boolean function in a form of, say, a max term, so how we can do it? Say we have a Boolean function like this one. We need to represent in the form of max term. So how we can do it? For the max term, we know that if there is a 3 variable system, then there must be a some z term here and some y term here involved in this one. So we need to add z here and we need to add y here. What we do is, from the postulates of the Boolean algebra, we know that if we write this thing, z into z complement, that is always equal to 0. So we can just write it here as z into z and z complement, and we will write here as y and y complement. Similarly, if we just apply the distributive law, you can open them up like this one and this one, because two of the terms are same, so they will finally result in the same thing. So now this function is represented in form of max terms like in this form. Say if we have another function which is represented as this one, again there is one term missing here and we have a one term missing here. What we can do here is that we need to expand this function in a similar way to the one which we solved here. We apply the distributive law here. We will expand it first in this form, and then we can again expand this one from the same law. here. Now if you should see that we have two terms common, so the final terms will be resulted in form of 3. Sorry, not common. This one will be replaced by the 1. So we will not write here. And now if you just try to expand this one on first only this one, you can see that we can expand it by writing this term, additional term here, because the resultant is always equal to 0. So we can express this expression in this way. Similarly, we can also expand this and this, and if we combine the result of this one, and this one, we will get the final value of f equal to as this one. And now you can see that if you all of these represents the all the terms. This, it has now x, y, and z. It is also x, y, and z, and it is both of the next term also have some component of x, y, z. So we now just need to represent it in the form of capital M, because in the max term we represent the equation of the Boolean function in form the AND. So these all the terms are ANDed. So this can be represented as M0, because it is equal to 0, 0, 0. This will be capital M0. This would be equal to 0, 1, 0, so which is equal to 2 here, and the next is equal to 4, and then next 5. So we can write the final f here as this one. So what we started with this function, in which we had only 2 terms, and both of the terms had one variable missing. So we first expanded it using the distributive law, and then from the distributive law we have in this form, in the standard form, in which all the terms are being ANDed, and this you can say the product form. And from this form, what we did for each of the separate term, this one, and this one, we calculated its whole value like this one, including the missing variables. And now once we have taken all the values, there were few common terms, and removing these common terms resulted in this final values. And you can see that from the min term or max term table, these values represent capital M0, capital M2, capital M4, and capital M5. So this function can be represented in a form of like this one. So this is because they are ANDed, so we can represent them using this pi symbol. It represents the AND operation between these terms 0, 2, 4, and 5. So we can represent this function in form of this one, or this one. All the three are correct answers. So in this way we represent any given function in form of min term and the max terms. Now we will look at a little conversion among the two canonical forms that we have discussed. Because we have told in the start that say if a function of 3 variables is represented in this way, m1, 4, 5, 6, 7, it means for all these min terms we have a value of 1 at the output. The complement function will be represented as the summation of min terms on which we have zeros, and which are these missing terms here, so 0, 2, and 3. And now if we apply the De Morgan's law, we can say that this function, if this function is represented in form of max term, then it will be represented as like this one. So the sum of min terms is equal to basically the product of max term. The sum here we're actually representing the OR operation, you can say, and the product is representing the AND operation. So you should be very clear that sum of min terms is equal to the product of max term, and we just only need to interchange the symbol of this and this. For the min terms we will be using this summation system and this symbol, and for the product thing or the max term we will be using this pi symbol. This will be represent summation for ones, and this is for zeros if you look at from the truth table. And you can clearly see that we will have this relationship among the min term and the max term, because for the min terms it is represented in a form of small m, while the capital M is representing the max term. So if you take the complement of the min term, that is equivalent to representing the max term. So if you have a function, say, which is defined as this in this form, say 1 4 5 6 7, then you can, if you have to represent it in a min term form, you can just write that it's the summation of 1 4 5 6 7, or it is represented as multiplication or AND of 0 2 3. So from a same table, you can just clearly, by viewing the table, you can just directly note that what is min term representation and what is the max term representation. Say if we have a function like this one, xy plus x complement z, we can first we need to represent this in a form of min term or max term. So we have derived the formula from which we can calculate it, and other ways that first we derive it through the truth table. So this is 3 input system. We will first have the 8 combination here, and by applying this Boolean function here, there is final result is here. We can see that if we want to represent this system in form of min terms, then that's equal to the summation or ORing of 1 3 6 and 7. If we just OR them, though we will get the representation in terms of min term, and for the max term we will look at the 0. 0 is at 0, place 2, place 4 and 5. So this is will be representing the max term representation. So for any given Boolean function, you can easily represent that in terms of min term or the max term just by looking at the truth table. Now we will see some other types of forms which are, you can say, known as the standard forms. Because if you see the canonical forms, in the canonical forms there is a limitation that for each term that you are representing, it should represent all the variables that are involved in the system. Say if it's a 3-input system, then all the terms must involve some form of the x, y or z, all these terms. But in usual way, we don't find it very convenient because most of the Boolean functions can be represented in say a single variable form or 2 variable forms, or the terms which involve a single variable, or terms which involve 2 variables. It's not must that all the terms must have all the 3 input variable. So we generally represent them in the form of standard form. In the standard form, we call it as the sum of product representation, which is like this. You can say these are the products, this one, this one, this one, and we are ORing them, so we call it as sum of product. While similarly, we can also represent a different function as product of sum. It means these are the sums, this is the sum, this is the sum, so we are just taking the product of it. So there are 2 separate representation which we call as sum of products or product of sum. And there could be a function which is say, you can say neither in any standard form. It's neither in the sum of product form or neither in the product of sum form. So we need to calculate something else from this equation to represent in any one of the form, which we will see in the next slide. Now we will be representing all these 3 functions f1, f2 and f3 in a form of a circuit diagram in the next slide. Say this is our function f1. What we have done here is that this is you can say a 2-level implementation. We call it a 2-level implementation of sum of product. So in sum of product, what we do is we first calculate, in the first step we calculate the step, and for the second step we calculate the product only. So you can say that this is the first step level and this is the second level. So first level will calculate the sum and the second level will calculate the product. And this we have represented in a way that we have assumed that all the complements are available to us in a separate signal form. Similarly, for product of sum form, in the product of sum form, We again can represent it in a two-level representation. Say this is the level 1 and this is the level 2. So this is level 1, this is level 2. In the first level we will be doing the product thing, and then the next one we will be doing the is something. So in this way we represent the system in a standard form in using the, you can say, a two-level implementation. And then there is a you can say a multi-level implementation. For example, for the last in the last slide we have done the this thing, the f3 function here. If you see this f3 function, it's neither in the sum of product form or the in the form of product of sum. It is in a different form. For because first you need to calculate AB and then you need to calculate DE, and because the result of DE is dependent upon the C, then you have to OR it with the result of AB. So it means there are actually, you see that there are three levels of implementation: 1, 2, 3. Because first we need to calculate this AB, and DE we can do it at the same time in the same level, but then after that the result of this D plus E should be ended with this C, so which is done in the second level, and after that then we can OR it with the result of AB, which is done in the third level. So you see that in this case the total levels of representation have increased by 1. But we can change this Boolean function in a way that, or we can modify it in certain way that it's become equivalent to more or less to our sum of the standard representation of sum of products or the products of some form. We can easily do that. We just, you can see that if you open up the parentheses, we will have the CD term here and the CE terms here. So now this is basically the sum of a product thing. We first need to take the product of this, this and this. We can take that in just a single level. So in the first level we can just have this one, and in the second level we will be ORing the result of all these three terms. So we have used the OR gate to OR these three. So this is how we represent the F3 term. We will be now representing a two variable system in form of 16 different functions, or 16 different binary functions which are denoted from F0 to F15. We will be seeing them in detail, that what are these 16 functions and how they are related to the two inputs X and Y. We have summarized these 16 functions here as this one, and you have seen that you can see that they are represented by a certain name like this one. They have certain properties. Some of them are represent the constant value, some represents the basic values or the operation or the complement one, other are related to the basic and or gates. There are many other things, properties involved in it. We have seen the basic OR and the AND one, so there is no NOR involved in it. Similarly, exclusive OR is involved in it, exclusive NOR is involved in it, and the NAND is involved in it. So all of them have different values representing, and their symbols are also represented here because we will be now using this NOR and the NAND ones. So you will see that we will be using these symbol for them. And if you see this table, then you can determine that 2 are for the 16 functions, 2 are equal to a constant, 4 are repeated twice. Inhibition and implication are not commutative or associative, while the other 8, complement, transfer, and or NAND, all these equivalents are used as the standard gates, because you will have done something related to them in the lab part 2. So these all are actually the physical gates that are available. A complement is just the inverter. We will also have the buffer, and the equivalence operation is represented by exclusive NOR. The Boolean expression and, or, and not, the expressions here are the not have the operator and or not, which are the basic one which we have discussed. And if you want to implement these logic gates, generally we tend to implement all the other the 16 functions that we have studied, or the other important gates that we have seen in the last two slides, like say the exclusive or and the exclusive NOR and the NAND and the NOR. We can represent all these gates using these three ones: the basic one, and, or, and the and not operation. And you have also seen that these are also used to represent any given Boolean function too. Say for this AND gate, we have already seen its table, and we know that it is represented, it will value is equal to 1 only when the both of the inputs are 1. Similarly, OR has output of 1 even when one of the input have a value of 1. Inverter is just the complementing the input here, and while the buffer retains the value which is present at the input. Similarly, we will be studying a few other gates like the NAND one and the NOR one, the exclusive OR and the exclusive NOR. These are also very commonly used. If you see the NAND operation, it is basically the complement of the AND operation, because in the AND we have only have one when both of the inputs are 1, and it is opposite to that. Similarly, for the NOR one, you can see that for the NOR one, if we either of the value is 1, then we will get 0 in the output. Similarly, we will have two other important gates like exclusive OR and exclusive NOR. In the exclusive OR, if the both of the values are different, and then we will get 1 in the output. While in the exclusive NOR, if both of the value are same, then we will get the output equal to 1. And kindly do remember these symbols, because we will be utilizing these gates very often in our next few lectures. Now we will see that when it is possible for us to represent any given gate or a given function in a form of multiple inputs, because we have so far what we have studied is all the gates have two input system, like we studied the AND or gate. We said that it was mostly for the two input system, but what if we increase its input from 2 to 3 or 3 to 4? What will this response will be? Generally, we say that we can extend any given gate to a multiple input if it obeys these two laws, the commutative and the associative law. And if you see the AND and the OR thing, you can easily know that for the commutative and the associative law are obeyed by the both the OR operator and the AND operator. So both of them can easily be extended to the three input case, but this is not true for all other gates. We will see in the next slides. If you see that for the NOR and the NOR gate, NAND and the NOR gate, they obey the commutative law, but the associative law is not obeyed. Because if you look, this is the example of the NOR gate. Because if you first have these XY, you first perform the NOR on the XY and then perform the resultant on the Y, you get this equation. This is a symbol for the NOR. But if you first perform the NOR operation on Y, Z, and then with the X, you will get this result. You can see that the both sides are not equal. So it means that it does not obey the associative law. And the same is the case for the NAND too. So it means that in a direct way, we cannot extend these NAND or the NOR into the multiple input system. But we can do a slight modification in its representation to make it representable in form of a 3 input or 4 input NOR or the NAND gate. How do we do it? Actually, what we do is we take the complement of the OR gate. We don't first take the x and y term and take its NOR and then complement its result with the z and then take its NOR. What we do is we just first simply take the OR of all the inputs, and after that what we do is we take its complement. So in this way our result will be the same if we take xy first or yz first, because we know that for the OR gate it obeys both the commutative and the associative properties, so it will also obey here. So first what we will do is we will first take the or all the terms involved in it, and then we will take the complement. So if we represent it in this way, then we can represent our NOR gate in a 3 input form. And same is the case for the NAND gate too, that for the NAND gate, if you look at this, if you separately take first x and y and then take a NAND of it and then take the again the NAND operation for the result of this with the z, you will not get the both side equal. But if you, what we do is you first take AND of all the terms that are input, all the that inputs that are involved, and then take the complement, then we can achieve this thing. To represent any given NOR gate in a, say if we are representing in any, say this kind of a function, we are representing this function, so 3 input NAND gate is represented in this kind of way. This is the first one, this is the NAND gate for the 2 input system. Generally you have we have seen that for this NOR gate and this NAND gate, we will see in the future slides and the future lectures that generally when we represent any given gates in the hardware, we usually prefer them to represent these all the gates or all the functions in the form of NAND and the NOR one. We will discuss that in detail in the next lectures. Now if you look at the exclusive OR and the exclusive NOR, and that how can they be represented if we are representing them in more than 2 inputs. Say we have a 3 input system, then how we can represent the exclusive NOR and the exclusive NOR gates. Both are commutative and associative, but there is a slight issue that because generally when we will see the hardware implementation of these gates, we will see that generally we don't implement these exclusive OR gates in a this kind of a, we don't get separate, you can say, IC or a single gate IC that represents an exclusive OR. Generally what we do is we represent the exclusive OR in the form of and OR operation. And most of the practical implementation where exclusive OR or exclusive NOR is used, we represent them in the form of a Boolean function, and then the Boolean function is then represented in form of OR and gate. So we generally don't represent this exclusive OR and NOR straightforward in a simple gate form. But for the today's discussion or this lecture discussion, we will be only focusing on this extension to the multiple inputs. Say we have a 3 input system x, y, z, then we can represent it in this way, that our exclusive OR is represented in this way, and if we can also represent it in this way. Now there is a, if you look at this truth table or the truth table of the exclusive OR gate, you will see that there is a slight change in the definition of the exclusive OR operation which we have defined before, because previously we have defined for the exclusive OR case that if both of the values are different, means one value is 0 and one is positive, then for that case we have a 1 at the output. But actually it's not that case. It's only that definition is only applicable for a 2 input system. The actual definition for the exclusive OR operation is that you can say that exclusive OR is an odd function. It means that its value or its output will be equal to 1 if the input variables have odd number of ones. So in this combination, whenever we have odd combination of ones, we will get output 1. So for this you can say that we have 1 here, you get the output 1. In this case, we also have a 1 here, only 1. This is two ones here, so these are not odd, so we will get 0 here. For the next one, we also have an odd function again that is representing here. For the next one, we have a two even ones here, so it will give 0. Again, we have two ones here, which is a even, so we will get 0 here. And for the last one, we have odd number of ones, so we will get 1. So the actual definition of exclusive OR is that for the exclusive OR operation, the number of ones in the input should be equal to the odd number of ones. If that's true, then output equal to 1, otherwise it will be equal to 0. So this definition is slightly different from the one which we use to study for the two input system, and this is also applicable for the 3, 4, 5 or the further exclusive OR inputs. Now we will be briefly discussing a few other things that are related to the representation or physical implementation of the logic levels. We have already discussed that we are representing the high logic as logic level 1 and the low level as logic level 0. This general representation is used in most of the hardware, and it is commonly known as the positive logic. While there is for some hardware there exists a negative equivalent, which is called as the negative logic, in which we have high is represented by logic level 0 and while low is represented as logic level 1. But in most of the textbook that we are following in this book, especially the positive logic is used. Say this AND gate represents a positive logic. Here is truth table is like this, and this represents negative logic here. For the negative logic, we often use this sign to show that we are using the negative logic, this one and this one, and it is represented as this truth table. Now we will discuss a little bit about the ICs or the integrated circuit, because IC is a silicon semiconductor crystal. We also called it a chip. This contains very small electrical components for constructing the digital gates, because it involves certain transistors level things to form a simple gate. It's not actually that we implement a simple logic gate like we represent an AND gate or OR gate. We implement it in the same way. Actually, when we are representing the final hardware or in a semiconductor device, they are represented by certain gate. All the gates are represented by certain transistors. There are various levels of integration for these things, which we call as the small scale integration, medium scale integration, large scale integration, and very large scale integration. These actually based on the number of gates that this can represent. Most of the currently used technology is this one, VLSI1, and which we use a very large number of gates to represent are embedded in a single IC or a single chip. Because currently you have heard the nanometer technology, so a transistor or millions of transistors are represented in a single IC or in a single chip. So currently we are in this era, the VLSI 1, and there are a lot of other improvements in it, not just the size but its cost and the most important, the power consumption. There are a few standards that are used in the circuitry. One is the basic one, or the you can say the starting one of the digital logic was the TTL logic. It's called the transistor logic. The other one is the ECL, and generally the ECL is preferred when we need a very high speed computation. And then we had a metal oxide semiconductor related thing, which is called the MOS, and after that we had the complementary metal oxide semiconductor CMOS. Currently most of the ICs or the gates or the actual transistors that are implemented are based on this CMOS technology. This is mostly used, and you have seen that the advantages of CMOS and its other derivatives like BiCMOS is that it required a very few area to represent a very large number of gates. it you can represent, you can have embed millions of gate in a single IC chip very easily these days. Then there are few characteristics that are also related to the some IC. These most common and then are the fan in, fan out. The other terms are the power dissipation, propagation delay, and the noise margins. We will be just focusing on probably few of them in the in our course. Mostly we will be using some delay. We will be discussing delay in the some of the lectures, but this is just for the reading, so just you understand that how a practical IC system or the embedded system of IC works. Then there are very computer aided designs that help you study the different representations like TTL or the CMOS and the other things, and how much area is required to represent a certain million level of gates, and how do you basically code a hardware. This is very important thing. Actually, it's not in the part of your course, but if you look at the title of your book, it involves Verilog, HDL, and VHDL. These are the two basically the coding standards for coding the hardware. In this, we actually design the hardware code for it, and then that hardware code is implemented on a chip to perform any given function. Just like say we have studied the Boolean functions. So to represent any given Boolean function, we will be representing that function in form of AND or gates through a certain Verilog or the VHDL coding, and then we will be implementing these code actually on some IC or some hardwares. And in the last few lectures of the course, we will be discussing a little bit about the ASICs and the FPGA, how these are formed. Kindly do read these pages from the book, especially the last integrated topic of the integrated circuit, because I have just briefly explained these things. It is not the important part of the course, but it is very good to gain a good understanding that how IC chip is manufactured and what are the basic components involved in it. Thank you so much.